Hi everyone, welcome to Gateway Lectures. Here there were the two questions. Yesterday there was a confusion for many regarding question number 2 and question number 4 of the day 9 quiz. They are the question from refrigeration and air conditioning. This was the second question, and a student asked me that it is given in the question that a condenser is entering into the subcooling region, and he asked me why we are taking into the why we are also considering the superheating region, and he also asked me if we are considering superheating region, that whatever the refrigerant part entering into the superheater will not have the heat from the refrigerator space. It might be having heat from heat exchanger. That was a doubt. So here I made a small correction in the question to just clarify the doubt. Everything question was the same, but I've added a last one more line here. Assume that refrigerator enters in compressor in superheated state. It was a statement added to here. You can just make note of this, and the solution, everything remains the same. Yesterday we did the solution exactly for this question, but during the typing we did not include this. Assume that refrigerant enters a compressor in superheated state. Here are the explanations. There are a few important things to understand when we are dealing with refrigeration questions regarding VCRS. Whenever it is said about supercooling and subcooling, superheating and subcooling, superheating will happen in evaporator section, and subcooling will be happening in condenser section. Suppose there are here 5 possibilities possible in the question. Whenever we are reading question, we should be very careful in knowing which among the 5 does the question fall in. It is also probability that there is no subcooling and there is no superheating at all. That is an ideal VCRS cycle. Even that can be possible. Even there is a possible of wet compression also. So if it is a wet compressor, then there is a possibility of the entry into the compressor can be even in the wet region also. So these were the all possible things. And there is a cases where in the wet region itself, our refrigerant enters into the expanded device. There is a possibility, right? So here we will see the few cases regarding superheating and subcooling. The first case is superheating in evaporator and no subcooling in condenser. Yes, this can be possible. As we said in question that wherever you see subcooling, you should take superheating. That is actually a wrong statement. The actual exact meaning to that I'll explain at last. The first, superheating in evaporator and no subcooling in condenser, as this can be possible. In the question they can mention there is only superheating in evaporator and no subcooling in the condenser. Yeah, then that can be the case possible. And for that case, our TS diagram looks in this way: superheating in evaporator and no subcooling. So in the superheating in the evaporator, so it enters into the superheated stage in the evaporator. This is a possible case. There is superheating in the evaporator. So these points actually will be 4, 1, 1 dash, 2, 3. So 1 dash is the entry into the compressor. That is the superheated stage, right? But actually it is said superheating in evaporator or superheating after evaporator. That can be possible. Superheating in evaporator. Here it is said superheating in the evaporator itself. So here the refrigeration effect or whatever the desired effect, since we can call it as simply desired effect. The desired effect is H1 dash minus H4. This is what yesterday we have taken in the question. So a student got the confusion. Why we are taking desired effect even after entering into the superheated region? Exact meaning is this: superheating in evaporator and subcooling in condenser, right? And one more case: subcooling in condenser and no superheating in evaporator. Even that case also be possible. There is a subcooling in condenser, right, and no superheating in the evaporator session. This is the case possible. And here this is 4 and this is 1. Here the desired effect remains the same. H1 minus H4 doesn't change. And next case, superheating in evaporator and subcooling in condenser respectively. He did not say that both should happen, but here both were happening. This is the case where yesterday our question was, right? So there is a superheating in the evaporator and also subcooling in the condenser. This was the possible case, right? And here the points were 1, 1 dash, 2, 3, 3 dash, 4. And here our desired effect is Since superheating in the evaporator itself we are having superheating, then it is H1 dash minus H4. And comes our last two cases for exactly both were the same. Superheating in heat exchanger, then it should have subcooling in the condenser also. If in the question it is given that the refrigerant after the evaporator or before entering into the compressor undergoes a heat exchanging process, right, and it is said that it is getting superheated, then always you have to consider equal and oppositely there is a subcooling in the condenser also, right. Whenever he mentioned the heat exchanger word in the question, then always remember there will be always superheating and subcooling both, right. Since similarly if subcooling in heat exchanger is given, then always it should have superheating in the evaporator also, so both will have vice versa. When it is given subcooling, it will have superheating. When it is given superheating, it will have subcooling when the heat exchanger term was used. So in that case, this will be our diagram. It will have the similar way, but there is a small correction here. 1 dash, 2 3 dash, and this is 4. But here our desired effect will be H1 minus H4 itself. Why not H1 dash minus H4? Because here superheating is happening in the heat exchanger, not in the evaporator, right. In the question, if heat exchanger is mentioned, then our desired effect will be H1 minus H4, that is from this point to this point, not from H1 dash. But in the question, heat exchanger is not mentioned, and it is said subcooling is happening, or in the condenser itself it is leaving from the subcooling region, then we need to consider H1 dash minus H4. Okay, so in our question yesterday, it was said 65 degrees and 32 degrees centigrade. Mean the entry into the condenser is 65 degrees and the exit is at 32 degrees, which is less than the Tsat, that is 45 degrees. So we said it is happening subcooling. And also this statement yesterday we were forgotten to add here. Assume that refrigerant enters the compressor in superheated stage. Right, here the condenser itself is having a in the condenser itself it is leaving at 32 degrees centigrade. Mean there is no heat exchanger. The subcooling is happening in the condenser itself. If there is no heat exchanger there, then here if it is said assume refrigerant enters the compressor in superheated stage, then it means that this superheating is happening in evaporator. Okay, this superheating is happening in evaporator. That is why yesterday in our question we have taken our VCR cycle, and here we assume this as 1 dash and 1, and here it is 4, and here it is 3, and here it is 3 dash, and comes here it is 2. And yesterday for desired effect, nothing but for the load given, the question load was given, right? Not exactly this question, but yesterday we assumed the desired effect is H1 dash minus H4 rather than H1 minus H4, because the superheating is happening in the evaporator itself, because the subcooling is happening in the condenser itself. There is no heat exchanger in the question. And also note this statement here. Yesterday we did not add, but here it is added. Assume that refrigerant enters the compressor in superheated stage. If refrigerant is entering in the compressor in the superheated stage without any heat exchanger, then obviously it should happen in evaporation itself, in the evaporator itself. Therefore, here this question is not a case of heat exchanger. But remember all these 5 note points. Whenever it is said heat exchanger, then always superheating and subcooling both should happen simultaneously. Okay, and there are possibilities for these cases also, 1, 2 and 3. Superheating in evaporator and no subcooling in condenser. Subcooling in condenser and no superheating in evaporator. Superheating in evaporator and subcooling in condenser respectively, as in our question. And one more question was a doubt raised by a student, and it was question number 4. It is about the Bell-Coleman cycle. And here in the question, the mechanical efficiency of the compressor, you watch the solution to that question. You also go through the question and watch the solution video on this question. In the question, it is given mechanical efficiency of compressor and mechanical efficiency of expander. And the student asked, and we was asked to calculate the volume handled by the air compressor. Okay. And the student asked me a question: why did we not consider mechanical efficiency of compressor and mechanical efficiency of expander? You note, remember one point. For our given data in the question, it is not a rule that the question being asked for us should always consume all the data given in the question. There are chances the data will be just given to confuse us. This is a case of confusion, because here it was said mechanical efficiency, right? So and one more thing, if it is mechanical efficiency, there will be no change in the TS diagram. The TS diagram remains the same, 1, 2 and 3, 4. Not even a shift in the line, it will be the same. So whatever question we have done, that is correct and it was the right approach. But to make the confusion clear, I will explain here what exactly is mechanical efficiency of the compressor and expander is. See, compressor is a device which increases pressure and temperature in the expense of work. By consuming work, it will expense the pressure and temperature of the whatever fluid we are using. Here we are using air, right? So compressor, how the compressor works, we will be giving electrical work input electrical work input will be giving to the compressor, and the compressor runs to increase the pressure energy, and also in the same sense increase the enthalpy, right? So whenever it is said mechanical efficiency, then always remember that mechanical efficiency, see, whenever we are talking about efficiency, means actual system there is some loss in the output. Suppose we are giving 100 kilojoules of electrical energy input to the compressor unit, and the compressor runs, but it is observed that it is performing only 80 kg of work on the fluid. 80 kilojoules of work on the fluid. Then where did this 20 kilojoules rush? The 20 kilojoules went into losses. What were the possible losses? There comes our mechanical losses or mechanical efficiency due to the losses. So here mechanical losses. What were all the mechanical losses possible? Friction can be a mechanical loss. Transmission line, the pipes. Friction can be a mechanical loss, and the rotating part of the compressor, there it might have some inertia loss, right? There are many possible bearing, the loss in the bearing, loss in the lubrication of bearing. So these all comes under mechanical losses. So whatever mechanical efficiency given in the compressor and expander regards to the mechanical losses, and there is nothing related thermal here. But one more efficiency for the compressor and expander is isentropic efficiency. If suppose in the question it is given isentropic efficiency of the compressor and isentropic efficiency of expander, then the states of 1, 2 will be changed. 2 will be shifting towards the side on the same pressure line to be 2 dash, and 3 will be shifting to the side on the same pressure line to 4 dash. Right. Since it is having isentropic, it is deviating from the isentropic path. Okay, so it is deviating from the isentropic path. Then our T4 will not be equal to T4 dash. Then yesterday whatever we have solved the question, that would be wrong. But in the question here, mechanical efficiency was used, not isentropic efficiency. Therefore, even under mechanical efficiency, our T4 will be equal to T4 dash, and T2 will be equal to T2, H2 will be equal to H2 dash, and H4 will be equal to H4 dash. So there will be nothing change in the question, change in the diagram also. Whenever it is mentioned isentropic efficiency, then we need to consider that there is a shift in the change. We will also solve questions on isentropic efficiency. Here in this question, the mechanical efficiency was given just to confuse between. Okay, the actual answer is whatever we solved in the question. This was a doubt raised by a student, so I made a clarification here. Even if you are having doubt, we'll discuss this in the Telegram group of Gateway Mechanical Engineers. You can just go get into the Telegram and search for Gateway Mechanical Lectures, right? There you will be getting the Telegram group. Join there in the discussion. You just ask the doubt you have. We'll be in a position to resolve the doubt. This was the basic explanation for the two questions which were the doubts raised. Thank you.